So good morning to all, both online and offline participants who are a part of this GIAN course on thermochemical conversion of biomass waste to bioenergy and value-added products. So we are starting our third day of session today. As promised, Professor Ang will be discussing more on microalgal biofuel production, that is 3G biofuel production in today's session. So without delay, let me welcome Professor Ang for this session. And Professor Ang, the floor is yours.
Hello. Okay. Yeah, okay. Good morning, everyone. So welcome back to the third day of our GIAN courses about the thermochemicals conversion about the biomass. So today, the topic that I would like to discuss is about the microalgae biomass. So how we going to turn the microalgae biomass waste into the biochar or maybe the bioenergy or bio products. So today I will start from more fundamentals, which I would like to introduce use about the what is the biochar. Biochar. So actually the biochar is the one of the solid products where we produce during the thermochemical process. I mean the solid products. So for any thermochemical production process, three types of the product that we produce. First is the liquid products, the solid products, and also the vapor or the gas products. So for the last 2 days, I focus more on the liquid products from the biomass waste or biomass into the liquid product. So today I will focus more on the solid product. One type of the solid product we produce is the biochar. So whatever name that you want to name it, the hydrochar, maybe with a relatively lower temperature, higher temperature, which I call it the solid product. So the end product, maybe we can call it the biochar. So what is the biochar? So biochar is one of the product that rich in the carbons, the carbon content from the biomass heat under the unlimited of the oxygen. This is the keyword. Limited. Limited of the oxygen. If with the oxygen, what will happen? Combustion. Combustion is will become H. Yeah, H. No longer the biochar product. So that's why this is very important. Throughout the thermochemical process, if you want to get the biochar or the solid product, that useful solid product must be under the limited oxygen or even no oxygen. Limited because sometimes the condition is very difficult with any no any oxygen, because in our air have more than 20% of the oxygen. So sometimes it's very hard to limit it to the total no oxygen. So that's why I said limited oxygen. Is possible, make it no oxygen. No oxygen. So if without any oxygen, so no any combustions might be happen. So your biochar product might be better. So it can be made by the thermochemical conversion, as I mentioned. Throughout the thermochemical conversion, there are many different types of the thermochemical conversion, which I will discuss later. So what is the main purpose of the biochar or the solid product, the end product? So first day, if the biochar without any further, what I mean is without any further treatment, we can use as the bioenergy directly, or can be used as the carbon sequestration directly, because why? This is the carbon rich material, can reduce the carbons, and can store the carbons, can be used as the bioabsorbent directly, bioabsorbent. So you can put the bacteria inside the biochar, so it can be the housings for the your bacteria or your fertilizer. So can be used as soil fertilizer. That's for the soil fertilizer. Is suitable to be used as house for the soil fertilizer. Can be used as the bio fertilizer, and also for the bioabsorbent can absorb some pollutant methods. So this is about the biochar. Then today the biomass that we would like to discuss is about the microalgae. So like Dr. Lamjia already mentioned, the microalgae is the third generation of the feedstock for biofuel and bioenergy. It's the third generation, because the previously the last today I'll be discussing about the non-edible feedstock. For the non-edible feedstock, we call it the second generation. Of course, the first generation is what? Yes, correct. Yeah, it's the edible feedstock which currently market are using. Still the first generation. Mainly focusing on, I can say the more than 85% are still using the first generation. So we need to explore what is the potentials of the third generation. We even have the fourth generation. Have you heard about the fourth generation? What is that? The fourth generation, a genetic modified microalgae. Yeah. Yep. Then for the microalgae, I guess most of you know what is the microalgae, because it has the high photosynthesis ability, and also the growth rate. It can be matured from the very beginning for the cultivation process until it's matured is normally less than 1 month, or normally it's just take, if for the Chlorella species, it depends on species. If for the Chlorella species, it takes maybe just 2 weeks, 15 days, until it's a maximum or the optimum productivity, just 15 days, 15 days. And also it's only it has a very high photosynthesis. Why the photosynthesis? Photosynthesis means it only consume what? Photo, sunlight. Photo is what? Sun. Correct not? Photo is sun, sunlight, and CO2. So during the cultivation of the microalgae is totally net zero emission, I can say, because it's used the what? Sunlight and also the CO2. It consumes the CO2 for the growth rate. So what is the main components for the microalgae? It has the lipid, protein, and carbohydrate. Of course, it has other components. So this is the main components consist in the microalgae. The lipid content, the protein, and also the carbohydrates. So how? This is the pathway. This is briefly introduced about the pathway from the cultivation of the microalgae up to the microalgae-based products. First is the cultivation. After the cultivation until it's matured, it takes about 2 weeks for the Chlorella species. Then after that, we can harvest it. Harvest, then rewater of the microalgae. Then sometimes you can see the powder of the microalgae, correct not? Then normally people culture the microalgae for what? For the pharmaceutical applications, to extract the useful compound from the microalgae for your supplements, correct not? Supplement. So after that, the waste microalgae, what you're going to do? Then this one, what we can doing right now to convert it into the some useful products. Then we can do the extraction, extract whatever that you want, and purifying. And after that, we have the microalgae based products for the pharmaceutical products. This and also the supplement. This is the main two products that currently the cultivation of the microalgae, the main purpose. Then after that, we also can be used as the biofuel, because why? The microalgae has a very rich in the lipid content. The lipid content can be converted into what? A biofuel or biodiesel. And also the carbohydrate also. Carbohydrate is one type of the, can be converted degraded into the what? Sugar, reducing sugar, then can be converted into the bioethanol as well. So it can be used as a biofuel. Then the biomass waste can be also used as the animal feed. After it drying, can be used as animal feed. That one. So this is a briefly introductions about the microalgae. So yeah, when we talk about the thermochemical conversion, now the main product is what the feedstock is microalgae, but it can be used in any type of the biomass. Biomass. You see. For the I divided into the three categories. One is the reaction environment. Reaction environment, that means whether it have the air or not. And I mean the oxygen, with the oxygen or without the oxygen. So you see, if with the oxygen, like all of you already know, the combustions or coal firing will be happen. If the combustions happen, that means what? Heat and or steam will be produced. Will be produced. So throughout the combustion process, the thermochemical combustion process, so we can generate what? The energy. Of course, you can generate the energy. Energy in the form of what? Heat and steam. Then can what? Run your generator to produce the electricity. The steam turbine to generate the electricity directly throughout the generator. Correct or not? So this one through the combustion. Thermochemicals are under the with the oxygen or the air. It's the combustion process that can produce the heat or steam. Then after that, heat or steam can we go through what? Your generator to produce the electricity directly or another sort of energy directly. So the energy is keep transforming. Then with the limited air, why the gasification is a limited air? Because you see, the main product for the gasification is what? Biosyngas. Biosyngas. We need some air. For what? To produce the syngas. To produce the syngas. Sometimes we need the first into the air, steam air, gas steam air to what? To get the more hydrogen. The more hydrogen, so that we can produce the biohydrogen throughout the gasification process. So that's why with the restricted or limited air, we can throughout the gasification we can get the syngas. Of course, the heat will be generated as well throughout the gasification process. So this is the two main products. Then the thermochemical process that we all know is what? The pyrolysis, the torrefaction or liquefaction. These three processes we keep discussing for the past 2 days, right? Not that one is with totally no air, with no air. You see, for the torrefaction, which is the I can say it's a mild pyrolysis, which the main product is what? The biochar. So this study we are using the torrefaction to get the biochar. Biochar is the main product. Of course, the byproduct will produce the liquid products and also the gas products little bit. Gas is really little bit because the relatively low temperature. So the main product is the biochar. The liquid fraction, we can get both biogas bio oil or biochar, or you call it the hydrochar for the liquid fractions, or the hydrothermal, we call it the hydrothermal carbonizations, whatever name that you want to call. Because why? What is the product that you want to focus, then you name it the process that the name. So actually the concept is the same. It's a liquid fraction. I mean, you go through the thermal process with the vapor form or the liquid form. That one we call the liquid fractions or the hydrothermal with the water hydrothermal. For the hydrothermal, the main product is the what? The hydrochar. Some of you want to get hydrochar, and some of you want to get the bio oil. Then a little bit of the what? Gas, syngas will be produced. The last one is the pyrolysis process, which most of the industry currently using the pyrolysis process to degrade the thing. So degrade the biomass. So the main product can be bio oil or biochar. Can be it depends on the condition that you want to focus on. Can be bio oil or biochar. Then the both will be produced as well. Then of course the biogas, good amount of the biogas will be produced. So from the industry project, I already discussed last few days. The biogas that produced normally we feed back into the burner, burner or the turbine, burner or the turbine for the pyrolysis process, because normally the pyrolysis process are run at around 500 degrees C. For the optimum, the minimum temperature to optimize the bio oil or the biochar is around 500 degrees C. So in order to run up to that temperature and maintain that temperature, the electricity that input is relatively high. If we just rely on the electricity, the overall production cost might be very, very high. So that's why normally we are feed back the syngas that produced through the pyrolysis process, because pyrolysis process is produce a rich amount of the syngas, or biosyngas, we call biosyngas. So that's why I can feed back to the pyrolysis reactors to run the pyrolysis process and to get your bio oil product or the biochar product. So for the pyrolysis process, three products that we produce. The amount roughly the amount of the three projects is range between 30 to 40%. It depends on your condition and your focus. 30 to 40%. Sometimes maybe 35% of the bio oil, 35% of the biochar, and another 30% is your biogas. Sometimes if you want to set the conditions to produce more defined biochar, maybe the biochar process biochar yield can be reached up to 40% or 45%, because your product is the biochar. You want to focus on biochar, and the bio oil are relatively maybe small. Then some amount, a little bit amount of the biogas. It really depends on the condition and also the raw material that you are focusing. So in this study, particular this study, we are using what? We are using the torrefaction, torrefaction. So torrefaction, they still divided into the two types of the torrefactions. One is the dry torrefaction, another one is the wet torrefaction. Wet torrefaction, we can call it the hydrothermal torrefaction. Hydrothermal, same with your liquefaction process. This one is a relatively low temperature. That's why we call it the hydrothermal torrefaction. So for those still don't know what is the torrefaction, is relatively mild pyrolysis. That's why I keep mentioning it's mild pyrolysis with a relatively low temperature, with happenings around 200 to 300 degrees C. For the reaction time around 15 to 16 minutes, depend on the product that you are focusing. With the torrefaction, we are able to enhance the calorific value and energy content, as well as the carbon content of your product. What is the product? Just remember, what's the product for the torrefaction? Biochar. Yeah, able to enhance the calorific values for the biochar. Because for this study, our main aim is what? To produce the biochar that can be used as a solid fuel. Solid fuel. As a solid fuel. Then it's able to reduce the moisture content throughout the process. So without to reduce the moisture content. So biochar is the main product. While for the wet torrefaction, we can use the water as the relative medium for the subcritical water that we keep in the liquid phase, but below the critical temperature of the water, because 374 degrees C at around 150 to 240 degrees C, with more than 5 bar, because with the water at the medium, once you heat up more than 100 degrees C, the temperature, the pressure will be increased as well. The temperature increase, the pressure will be increased. So normally it happen more than 5 bar to 10 bar. If we run at 160 degrees C, easily it can up to 10 bar. So it is an attractive method to convert the wet biomass into the biochar without the drying process. Because this one is drying process, because the microalgae normally are in the wet form. So we don't want to waste the energy for the drying process. So that's why. Or we can dry under the sunlight, but it takes few days. Then we choose this process. We see what is the feasibility of this process. Yeah, problem statement. So in order for you to conduct the one research, this one if academic research, you need to figure out what your problem statement. What you want to solve? What is the problem that you want to solve? So high demand of the non-renewable energy have created the energy crisis. This one is a general form, but microalgae biomass has a relatively low carbon content because we want to convert into the what the solid products. No carbon content, low energy content, and low calorific value is not suitable to be used as a fuel. The hydrocarbon, not because the fuel. What is the fuel? Fuel content of what? C and H, hydrocarbons. So low calorific value. So the high moisture, because high moisture, you know, because microalgae culture in the water require for the non-renewable energy to dry before the thermochemical process. It goes through the thermochemical process and need the drying process. Thermochemical process that we mentioned here is like the pyrolysis. Normally we are using the pyrolysis or even the gasification. Gasification also need to be dry. So bio oil produced from the microalgae pyrolysis has been a disadvantage, including the low chemical and thermal stability with the high oxygen and water content. Have very strong acidic which limit the energy application and development. So because from the previous study we found that for the biomass, the microalgae biomass, after the extractions, the waste, then we want to try to convert or extract the bio oil. It's very difficult and the quality of the bio is not very good. So this one I think yesterday or the day before we mentioned about the microalgae. Microalgae, yes, the microalgae have the highest yield per land area, per hectares, per land area. But during the extraction, it's very difficult. The amount of the extraction is maybe just around 10%. I can say 10% of the microalgae, the weight of the microalgae. For example, you have 1 kg, you only can extract out how many? 100 yeah, 1 ml. This one is an ml, not liters. Then in order for you to get 1 kg of the microalgae, you need to have 1 kg. How many? I don't know how many liters already. Normally is 10 grams per liters. 10 grams per liter of the water. It's a very big pen. So that's why. But in overall the year still highest. Then the microalgae will get contamination easily if we have the large scale cultivations, open pond large scale cultivation. Okay. Then the reactor design and scale up for the pyrolysis require the appropriate kinetic study to understand about the biomass. This one. In this study, we also embedded some kinetic study to understand what is the biomass reaction. So to see what is the suitable temperatures for the hydrothermal process. So in this study, we have 3 objectives. First thing, we still investigate the dry torrefaction. We need to compare because we know that the dry torrefaction will produce the good product because it's totally dry. Correct or not? Then we have to compare with the advanced wet torrefactions. Okay, why I add the advanced, the word advanced here? We are using the microwave. Microwave. This one advanced is a microwave. We are using the microwave. So we compare these two processes. What is the difference between these two processes? Compare with the same feedstock. Why I compare the Jatopa biomass? This one, the Jatopa biomass is what? You still remember, I'm doing the research about the Jatopa oil. Then this one is the Jatopa, the oil biomass. The leftover biomass. So we want to see what is the effect. Then after that, to analyze the effect of the torreference on the microalgae using the advanced TGF-TRL, PY-GCMS. That one is what? We want to see. We want to see in details what is the effect of the torrefaction. For example, the TG. The TG is we install the TGA before the FTIR to what? To heat up the microalgae to the desired temperature. Desired temperature is what? Our torrefaction temperature. So that it's go through the simulated pyrolysis process. Then at the same time, we see what is the product we can get. At which temperature, what type of product will we produce. Then so that when we want to conduct the torrefaction, we know what is the temperature that we can heat it up so that we can have the certain targeted product. That's the thing. Similarly, for the PY GCMS also same. We want to see what is the product. So the for the PY GCMS, we even conduct the double shot. Double shot, that means what? Double shot, that means 2 times of the pyrolysis. 2 times of pyrolysis is what? The first time is the pre-treatment of the lower temperature, which is the torrefaction. Then followed by the what? Followed by the pyrolysis. See what is the product. So compare with without the pyrolysis. No, without the torrefaction process. So what is the product that we change? Later on you will see the result. It's different. After the torrefaction, the product that you get might be different. So lastly, we want to see the effect of the wet torrefaction on the pyrolysis kinetic using the microalgae using the independent parallel reaction. This one is a kinetic study. So this one is the methodologies for objective respectively. These are objective 1, 2, 3, 4. This one is the dry torrefaction like usual. In this study, we are using two types of the microalgae, which is the Chlorella ESP31. ESP31, what you need to know, you don't need to know the scientific name. ESP31 is you need to know is what? High in carbohydrates. And another one is a FSP, is high in protein. This one you need to know because this one will affect our result. So high in carbohydrate, then what is the outcome? And high in the protein, what is the outcome? Why we have the Chlorella or the microalgae with high with the protein? Because as I mentioned, the industry want to culture the algae to extract the protein. To extract the protein. So that's why we want to see what is the effect. Of course, we compare with the total biomass. See what is the effect. With the torrefaction temperature between 200 to 300 degrees C for 15 to 16 minutes. Then we analyze the few properties, analyze the characteristics, and also the torrefaction severity index. This is the dry torrefaction. And compare with the what? Wet torrefaction. Wet torrefaction, we are using the microwave reactor. We are using the microwave reactor. Then with the acid solution, we use the organic and also the inorganic acids because we want the acid hydrolysis to take place. So after we putting the acid and without the acid, the pathway is reaction pathway is different. Then conduct at the wet torrefaction at 160 degrees C and 6 bar. And similarly, we analyze the few properties, the chemical, physiochemical properties, and also the hydrolysis composition of the product. This is the then after that we compare between the dry and also the wet torrefaction. What is the difference? After that, we also study in-depth analysis. In-depth analysis, just now I mentioned, we want to see what is the effect of the temperatures towards the product, the microalgae biomass product. So that's why we have the real-time gas analysis. Real-time means what? We heat it up. At the same time, the product, the gas will be heat sending to the FTIR to capture what is the product, the real-time product. Similarly, we have the single and double shot of the analysis and go through the GCMS. GCN. Single shot is what? Single shot is directly do the pyrolysis, or double shot is up torrefaction then pyrolysis, and see what is the difference. What is the product difference? Then we can see what is the product distribution of the protein, carbohydrate, and lipid. The protein, the carbohydrate will produce what? The protein will produce what? And also the lipids will go where? Yeah, this is what we study. Then after that is we study the kinetic study, the kinetic model. The main purpose for the kinetic model is we want to see the activation energy. What is the activation energies for the product, for the samples. Later I will show you what is the later I think later we'll show you. So this is the initial property, so that's why I mentioned when you want to analyze the certain samples, you need to know what is the compositions, what is the possible analysis, and also the element analysis. So this is the two type of the microalgae. You don't need to know the scientific name. You just need to know it's the Coretta, the ESP31, rich in carbohydrates. For the carbohydrate, this is your Coretta, the CV. Then another one is this is the modified microalgae. Microalgae still Coretta, but it's modified. Name is as the FSPE. This one is rich in protein. Because the pharmaceutical company they want to extract the protein. This one is rich in protein. So this is the HHV and also the hydrogen to carbon atomic ratio. This one we done it on the element analysis to see what is the CHN and O. CHN and O. Okay, to calculate the ratio. This is the microwave analysis. As I mentioned that we modify the household microwave, then design this reactor to control the pressure and also the temperature, and put in the nitrogen gas so that it's free from what? Oxygen. Free from oxygen. 2 biomass samples with just one condition, but in this study we study the difference liquid mediums which is using the acid, water, the sulfuric acid, and phosphoric acid with the different acid concentrations. So this is a microwave vector reactions. This one is the what? To analyze the microalgae potential composition. Yeah, because this one is a raw and wet torrefied microalgae. This one go through the wet torrefaction. Then after that, these two study. One is the TGA. After the TGA, then it go through the FDR directly. Then we can know what is the peak to guess what is the potential product. The potential product TG. Then this one is the what? Single and double shot of the pyrolysis. Then connect to the what? To the GCMS directly. This one we heat it up here. The pyrolysis to simulate. Sorry? FDR, yes. Or this one we convert two acids to see what is the peak. Yeah. You see FDR, we only can see the bond. What is the bond only? The bond, I mean the carbon, for example, the carbon to O, C and O, the peak is the C and O. Functional group only. We only can know the functional group, then we guess what is that. Then compare to the standards. Yeah. Yes. Yes. slide number 14, yes. Yes, correct. Yeah. No. Okay. This one, because this one is not the pressure reactor. Not the pressure reactor. That means what? We cannot control both pressure and temperature. Either you control the temperature, the pressure will follow. The pressure, we just measure the pressure. What is the pressure? We didn't control the pressure. Either you want to control the pressure, then measure back the temperature. That's it. Because this is not the pressure reactor. If the pressure reactor is very expensive, and you can control both pressure and temperature as you want. Yeah. This one is not. This one is just to avoid that the pressure of the reactor up to the certain limit, then it will release the pressure. That's it. We are not controlling the pressure for this reactor. Release the pressure in case of the pressure up to the certain pressure, certain critical pressure. For this, if not mistaken, for this reactor, the maximum pressure that can take is 20 bar only. 20 bar. If it reach up to 20 bar, it will release. You understand? So to avoid it not control the pressure. Yes, in this reactor, we can control the pressure, but after we control the pressure, we cannot control the temperature. Temperature and pressure you only can control because they are the correlation. You understand? Because with the liquid samples, cannot high pressure, not high pressure. This is not the high pressure reactor. Ah, 20, yes, correct, 20. Just to read the pressure. Then for our this experiment, so that's why we cannot heat it at a too high temperature. If more than 200 degrees C, the pressure definitely more than 20 bar. And more than 20 bar. So that's why we run at 160, 170 only. Because our reactor cannot take at the high pressure. Yep. And cannot control. No, can control the pressure. Either we can control pressure or temperature. Or that's all. Cannot control both. Yep. Flow rate. This one, the flow rate is not important because we put in the nitrogen. Then after that, we let it react because this is a closed system. We put in the hydrogen until there are no any oxygen. We put in until a certain time. Then we push out the oxygen. Then we off it. Not continuous. This is not this is the best reactor. Yeah. Best reactor. Not continuing reactor. Not continuing reactor. This is the best reactor. One best reactor. Yeah. Oh, function. Later I tell you because the function is what we want the hydrolysis happen. Hydrolysis took place during the reaction. During the reaction, we want the hydrolysis took place, which the acids can these all acids can provide you with the H plus. This one function. Yep, acidic. So that the acid hydrolysis took place. Yep. No. We fix at a certain amount of the liquid amount. For example, this one I can't remember how many percent already. Maybe if not mistaken 50%. For example, the dry biomass is 50% and the liquid sample is 50%. And also the what acid I can't remember how many the amount already. But what we want is the acid hydrolysis took place at the same time, so that it can modify the biochar that you produce, so that it can increase the porosity of the biochar. Because the acid hydrolysis will took place, so that the reaction later I will show you. Wait a minute, I think I show you here or not. this is the pathway. So yeah, so this is the pathway. That means you see, if we put the acid hydrolysis, the glucose will produce. Glucose produced, then we have the 5-HHM. This is 5-HHM is another chemical product, chemical product that useful in the industry. This one is another. So that's why I put in the H plus. The pathway is totally different without the hydrolysis. This one thing. Second thing, the biochar. The biochar will be in the different properties under the SEM. So this is a pathway. So it is a pathway based on our result. This one. Then we believe. This one we don't know. We just believe. Oh, this one, the carbohydrate will change to the sugars. We have the furans and also the ketones. This one we believe from this all analysis. Yeah, we believe this one will come up. This is the pathway that we are following. So that's why before that I keep mentioning you need to design your process so that the process can push towards the reaction that you want. One process, so many reactions will be happen. We don't know which one is happen. But through the further analysis, maybe we can guess. Oh, maybe this one. Why? Because through the STR, we know the functional group. Hey, that is the potential product. That potential product maybe is the furans. For example, maybe this one is the have the aromatic compound. For example, because we see the functional group. Hey, this one is from the aromatic compound. Maybe it's already follow the pathway. For example, yep. So that's why we need to design. So the lipid maybe it's converted into the fatty acid, but for the lipid is quite direct because lipid normally if you go to the fatty acids, that one is quite direct. So it's go through the cracking process. Yep. So this is the pathway. So we have the secondary cracking also. This. Yep. So so how we going to know? So through this one, the detailed analysis, because from just the normal hydrothermal process, this is the industrial process. Hydrothermal process, we don't know what is the pathway. We only can see what is the end product, but what is happened in between, we don't know. We don't know. So that's why throughout this analysis, further analysis, then we can know, we can guess. Oh, what is that? We can predict out. Yep, that's the thing. So anything. You see this one. We do the two state of the thermal degradation. First shot is about 200, 250, and 300. Why? Because this one we want to do the pre-treatment, torrefaction. Then followed by the second shot is the what? Pyrolysis. Then see what is the process. Yep. Pyrolysis. Then see what is the difference. First shot and the second shot. Yep. Correct. After the first shot, complete analysis. Then after the second shot, complete analysis. This one is the no. Yes. In this study, first shot we do the analysis. After the torrefaction, what has happened? Then the second shot, what has happened? Then without the first shot, that means the directly go to pyrolysis, what will happen? So that we can compare what is the effect of the torrefactions. What is the effect of the torrefaction? Yep. So that's why. Some of you asking me, whether what is the pre-treatment process? What is the process before that we want to do conduct before we go to the our product? So we need to see what is the pathway. So this analysis is very important, so that we know. If you want to do the hydrothermal analysis, not hydrothermal, sorry, thermochemical analysis. Yes. Different. I can say it's different, totally different. Okay, one thing different. Very simple. After you do the first shot, the water will be removed. Correct not? The water, because water 100 after 100%, the water will be removed. Then some other compound will be removed. so that the activated energy for the second shot might be much more lower. Much more lower. So that's why sometimes first shot is very important. It depends. You not necessarily to shot. It depends on the product, the sample, and also the product. See what you want. Sometimes it's not necessary to be that precise. If you get your desired sample, desired product already. Not necessarily, you know. Sometimes not necessarily. You can directly do the price. Hey, the bio oil that I get, this is what I want. And no need to do anything. No need the first shot or second shot. But we are doing the scientific research. We want to know what happened, what is the potential is happening, and we do this study. Yep, that's the thing. Or sometimes so that we can design more precise pathway towards certain products. Then we can explain to people, oh, this one happened. What happened during the thermochemical process? Yep. Besides the degradation. So normally for the thermochemical process, even though you didn't do in this detailed analysis, what you need to do is you using do the TGA. TGA. You do the TGA, we can know what is the thermal degradation temperature for the certain product, right? Not thermal degradation, whether it contains high moisture or it contains high cellulose content or the hemicellulose content. So what is the degradation temperature for that compound? Because from the TGA we can know. So normally we are conduct the TGA. Then from the TGA, we also can figure out if TGA you heat up to 900 degrees C. You also can know what is the possible analysis, right? Not possible. You can know the moisture, the ash content, and the volatile matter. What is the percent of the volatile matter, right? Not. Yeah, that is the alternative way in order for us to analyze the possible analysis. Then after that, it is good you go through the element analysis to know what is the C, H, and N. Sometimes sulfur, if any. If not enough, CSN is enough. Oxygen is the, we just assume the balance is oxygen plus the N. Yeah, that one is the element analysis. Analysis. Sometimes we didn't measure the S, Y. Sulfur is no, because for the normally for the sulfur is relatively low. That can be ignored sometimes because. And one more thing is most of the element analysis don't have the sulfur because it don't have the sulfur. Then this is the three important elements. And of course the balance is oxygen. Yeah, the balance is oxygen after considering the ash. Yeah, that's how we analyze the element analysis. Then before we go to any thermochemical conversions. Yep. So any questions so far? Oh, this one we use the raw and also the wet torrefied microalgae. We use both. Oh, this one. I think this one we conduct one only. Okay, why conduct one only? Okay, because I didn't go until result yet. You don't know. You see, initially you ask at one. Initially, we test on 3 samples. Correct not? 3 samples, including the topa. 3 samples. Correct not? 3 samples. So after that, we found that we didn't the jatopa we didn't further analyze in the second wet torrefaction. Why? Because we found that after we conduct the wet dry torrefaction on the jatopa, they are not much effect. So no use to do the treatment or the dry torrefaction on the jatopa. So that's why we didn't continue with the jatopa in the wet torrefaction because they are no effect. If no effect, I believe if we conduct the wet torrefaction also there are no any effect. So we didn't continue with the jatopa. Then after that, we conduct the wet torrefaction. We found that the high in the protein microalgae have less impact as well because our product is biochar. So less impact. So yes, less impact. I mean, the degradation will not take place because the protein will not degrade at relatively low temperature, because this one we just conduct at 160 degrees C. No effect at that low temperature. So cannot. Yes. That's why I didn't continue to do further analysis. Yeah. Because no effect. Not effect, I mean, doesn't mean that no any reaction. Less reaction. This is not what we want. Less reaction. They have some reaction. They have some degradation as well. Yeah. Yep. So that's why until the third one, only one sample. One sample, which is the ESP31, high in the carbohydrate content. Yep. Okay, this one is the first one, the dry torrefaction. This one is the very common tube furnace. This one very common. I think most of you know. Tube furnace with the puff in with the nitrogen gas. We control the flow rate using the 3 sample, which is the 2 microalgae and 1 jatopa. Then go through the gas. This one goes through the gas washings. This one this one we conducted in 2018. The reactor we already upgrade. We already installed the condenser. Condenser system, 2 state of the condenser system. Then we can correct the bio oil. Can correct the bio oil. In this project, we just focusing on the solid product. Yep. So this one is just the thermology, the torrefaction performance. Later on, I will discuss what is the solid year, what is the HHP. So this is the HHP improvement and also the energy yield. So this is the raw data, not necessarily to know. So we just know that if the temperature increase, the solid year will be decreased. Then with the increase of the holding time, increase with the holding time, the solid year will also decrease. So what is the summary from that one? So both of course all the jatopa or the both microalgae will be converted into biochar. Biochar. Yeah, we convert, sometimes you want to convert into the biochar, we convert, but the product is good or not, got effect or not, we don't know. That's the thing, can be convert, of course. You conduct any experiment, can be convert, can be because it's transformed already. Throughout the process, it go through some process, but the product will be improved or not improved, we don't know. We don't know. But after the further analysis, we found that what dry torrefaction has less impact on the FSP, the high protein one, and also the jatopa. Jatopa, why? Due to the lignins, the lignin contents, due to the different chemical composition, different things, the protein and also the lignins cannot degrade. That's why. But can be converted into the biochar? Not can. But if you want to if for the microalgae ESP, the HHB, the heating value will be increased 45%. Then the energy yield can reach up to 80%. Can be achieved with the torrefaction of the at 300 degrees C at 60 minutes for the FSP. So the richer result, you can download that paper. Then while for the wet torrefaction, you see wet torrefaction. This is the solid years. For this one, we using the water and also 3 type of the acids. You see, with the adding the acids, the biochar or the sample, not to say the biochar, the microalgae are further degraded, so that the total solid year will be reduced. Main is the further degradation will happen. But you see, for the FSP, for the wet in the wet for the FSP, even we add the acid medium. So they are nothing different, not much different even. So that's why we didn't continue. I see, not much different. It obtain the higher, mostly of the protein still remain. We believe is the protein still remain. So this is the HHB improvement. Let me see. Okay, HHB improvement or enhancement. You see, just now I mentioned that at torrefaction at 300 degrees C, the HHB are improved 45%, right now 1.45. But this one can be achieved by using the wet torrefactions with the sulfuric acid at 0.05 at only with the reaction time 10 minutes. If I'm not mistaken, this one just 10 minutes at 160 degrees C. It can achieve with the almost similar result by using the wet torrefactions. Yeah, that's the thing. So this is the comparison. Similarly, for the SSP, there are not much impact, not much improvement as well. This one. But the result will have the similar result, which means what? I make the conclusion or not? This one is the element. And which means what? The wet torrefactions with the microwave assisted wet torrefactions able to achieve whatever the dry torrefaction that can be achieved at 300 degrees C for 60 minutes, 45 to 60 minutes. This one with the microwave assisted wet torrefaction, it can be achieved by only 10 minutes at relatively low temperature, which is 160 degrees C. This is the conclusion I want to make from the experiment. So of course, this is the element analysis. We just found that the H content will be reduced. H content will be reduced. That means it's good for the combustion. If you want to use as a solid fuel, the H will be reduced. Of course, this one the CSNO. CSNO. Why we say the by differentiate? That means we just assume the balance is O. Then of course, during the process, glucose and byproduct will be produced. This one through the analysis, the glucose and also the byproduct will be reduced, will be produced. You see, this one we don't know. We found that the glucose is produced because the further study, the next study, we further do the further analysis on the glucose. I mean, go through the fermentation, can produce the bioethanol, the bioethanol that can produce up to 7%, which is a very good amount compared to this one. This one we don't know. We found that the glucose will be produced at the same time. 5-HMF will be produced as well. This one is one of the very important chemical in the chemical industry. So this is the TGA, just the normal TGA, thermal degradation of the this sample. This one is raw and water. The raw sample with the water. So I believe as the first stage, the degradation is the carbohydrate. Then the second stage is the lipid content. Then the last stage is the carbonate matter. So before that, you see, the degradation rate is highest as the first stage, which is the carbohydrate will be degrade for the raw and also for the raw or for the water samples. Water sample. That means that carbohydrate can be degraded already. So that means what? That means they are still degradation. Okay, we see the second one. It's for the second one. We found that the highest rates degradation is at the stage number 2. Stage number 2, which is the lipid content. The lipid content. So the carbohydrate will be degradation of carbohydrate is not so significant at the after we adding the acid solutions. This one is related to the later on. Yep. After the wet torrefaction. Yeah. Or these are TGA after. So that's why that means what? You see, this one is the second stage after the wet torrefaction, that means what? If we want to do the thermochemical conversion, we no need to degrade the carbohydrate already. So the torrefaction, wet torrefaction or torrefaction is a very good is very good method, very good pre-treatment method before we go through the second process, because it less the energy required for the degradation is less compared to the raw materials. Raw materials you need the energy to degrade for the carbohydrates. So it depends on the product. What is the product? So the wet torrefaction is one of the significance pre-treatment for the certain process. So you can consider the wet torrefaction as a pre-treatment if you want to target certain products. So this one is the TGSDIR. We found that at the earliest stage is they are nothing much from the gas that they can produce, but the CO2 significant decrease after the wet torrefaction, especially in the acidic solution. That means what? Your gas product is a cleaner product with less CO2 we produce. This is what we found. Then the intensity of the CH absorbent burns have been improved, enhanced due to the high lipid composition. Yep. So this one CH is what? CH is the, if not mistaken, CH is the methane gas. CH, yeah, we believe it's methane. The methane gas is increased after the after we using the acid wet torrefaction. Yep, methane. So the syngas will be produced. So this is the pathway that we believe will be took place. Yep. Now, so with the wet torrefaction, we have the acid hydrolysis, which the glucose will be produced, and also the second stage of the hydrolysis, the 5HM will be produced. Then the lipid content can be converted into the fatty acids or to the hydrocarbons. So this is the first study. I have another study. I continue from this study. So that study has more more detailed study about the microalgae degradation. So with this, we found that the HSP will be increased by 45%. If you want to use the microalgae biochar or solid product as a solid fuel, it's possible because the HSP is increased 45% by using the wet torrefaction process for 300 degrees C at 60 minutes. While it can be achieved by the wet torrefaction at 160 degrees C with the 0.05 more of the sulfuric acid. Yep. So for the dry torrefaction at 300 degrees C, not only remove the carbohydrate products in the bio oil, where the lipid product was also eliminated. So most of the carbohydrate product in the pyrolysis oil was reduced by 0.39% after pre-treatment by the wet torrefaction. And the activated energy for the carbohydrate was decreased already. For the microalgae pre-treated in the water or sulfuric acid. So in this, the activated energy of the protein and lipids of the microalgae was increased. It means it's become more stable. In short, the microwave assisted wet torrefaction at low temperature is an effective pre-treatment for the microalgae. It is good to be used as a pre-treatment process, which can be scaled up in the future research. So this is what we draw out. We still have some summary. So yeah, the wet torrefaction process can be produced two products. This is the recommendation. Recommendation summary. Because the whole product, because we found that the glucose is produced in the future, we can convert this sugar into the what? Ethanol. So low temperature vectorization of microalgae can effective reduce the energy input for energy productions, and also experiment of this one on kinetic beneficial for the reactor design. So if we do the, because in this study I didn't to this slide, where is the kinetic? I didn't show you the kinetics because the kinetic study is one of the very beneficial for the reactor design, because we know what is the pathway that you want. Then you can design precisely with the products that you are desire. So better understanding of the biochar production using the microalgae, the third generation of the feedstock. Then this methodology can be applied with the high carbohydrate biomass. This one is showcases for the as the fundamentals for the high carbohydrate biomass. If in the future you have the high carbohydrate biomass, then you can consider the torrefaction for large scale production with any minor modification. Of course, we need the modification, because why? Every feedstock has a different characteristic of the current models. So this is the main reference we are using. Oh, this one is another one. Yeah, this is the pyrolysis kinetic. Pyrolysis kinetic. We can know what is the activated temperature. Yeah, this is the TGA. TGA for the dry torrefaction. So similar, we get the similar result because the first peak is about the carbohydrates, Then for the Japodopa is the hemicellulose and cellulose, the lignin as the last one. Yep. So any questions? Any comment? Kinetic study, you follow, you see which model are closer to your degradation. You have to choose one model. If not mistaken, the models that we are following are the what? Arrhenius. Arrhenius, yes, Arrhenius. How you know? Yes, we are using Arrhenius models. Arrhenius models for this study, because it's close to our degradation curve. Yes. Then after that, okay, we need to plot. Okay, using the Arrhenius model, we plot the curve. Then with your experimental data, we compare. What is the percentage of the error? If the percentage of error is small, then you can mention that, oh, your model is your this experiment is follow that model. Yes. You need to plot the graph and see. Plot the graph. Then Arrhenius evaluation is very good for the thermal degradations. Yeah. Yes. Sorry. Yeah. Why 3? Oh, okay. Why is the criteria I choose? Okay, I choose this 3 acid. Okay, this 3 acid. One is the strong acid, one is the organic acid, one is the amino acid. That's why I need to compare. Yeah, that's it. And these are all the common acids. I didn't do the optimization. This study I didn't do the optimization. Yeah. Future we can do. Yep. I didn't do the optimization. Can because I didn't further study about the biochar or modify the biochar for other purposes. Can be used as an activated carbon, because in this end we want to use as the solid fuel. So that's why we focus on HHP. Can be used. Then the next study that I want to show you is that biochar we are using as a bioabsorbent. That one. Can we use the activated carbons? Yep. Porosities, yeah. Porosity, no matter what is the biomass, the porosity will be increased after the thermochemical process. Yeah, after the thermochemical process, if your increase, it's only how much is increased only. What is the total surface area? That one is the detailed study about the materials, material study. Yes, for me, I didn't go into the very detailed material study. Then you can conduct the SEM to see the surface area. What is the total area, total surface area? Yeah, correct. So to see the porosity, how big the porosity, we can know. Then before, after the porosity, how much is increased the porosity? Yeah, we can know after the further analysis by using the SEM. Mainly is for the biochar is the porosity. Porosity, why? Porosity, it can accumulate for example, the bioabsorbent you want to accumulate what? The good fertilizer or bacteria, so that it's not washed out by the waters or whatever. It's become like the housing for your fertilizer or for your bacteria. High porosities, normally high porosity, good for agriculture and good for the bioabsorbent or bio storage as well. Storage, but the storage another I got another problem. You can store, then how you release? Store then release, how release? Okay. 24. Okay, sure. Yes. Yes. No, this one is the biochar. Biochar. This one is element acid. I consider dry ash free. I didn't consider the ash. What do you mean? Sorry. Not without the ash of the biochar. Only biochar only. Yeah, biochar. Just the biochar. Not the ash of biochar. It's the biochar. Yeah. It's the biochar. Yeah. If for the upskilling, no, for the industry process, it depends on what you want. But for the industry process, not for me. I not recommend to add the acid. If add also very small amount. Yeah. If for the industry process, this is the scientific research. Yeah. Yeah. For the industry process, for me, I didn't add acid. Yeah. Okay. Microwave pyrolysis. For me, I didn't do the microwave pyrolysis yet. I didn't. First thing, I don't have the reactor lah. Let me tell you, I don't have the reactor for microwave pyrolysis. It can reach up to maybe 500 or 600 degrees C. I don't have, so that's why I didn't do. I didn't conduct. And the main thing is what you know. The main thing is your reactor. How until now you can tell me if you find a way, how to design the reactor, reactor, that can go through the microwave and can stand for more than 300 degrees C. The maximum reactor I can design is 300 degrees C that microwave still can go through. Then more than 500 degrees, mean the laboratory reactor. But for the industry, we can put just the conveyor belt and also the microwave sources inside the reactor. That one doesn't matter. What? Correct. What I mean the lab skill, how? I didn't find a materials yet. I mean the lab skill for the lab skill. Because why? I cannot design, for the lab skill, I cannot design for the more than 2 or 3 liters. Why? Because our sample is relatively small. I cannot get because we need to repeat a lot of experiment. Later you see how many points I plot, for the one experiment. So I cannot afford to have a big reactor for the lab skill. but for the industry scale, yes. So you tell me if any material can go through for the microwave, then can stand up to 300 degrees C. Currently, the material I found is just 300 degrees C, cannot stand more than 300 degrees C. I mean for that scale. Pressure is one thing. Second thing is the temperature and pressure. Like these two things. Yeah, both these two things. These two things. Yeah, yeah. Because the only material that I can find is the what for the very small scale. Yeah, very small scale. That means 5 to 10 mm. Yes, 5 to 10 mm. 5 to 10 mm. That one is mostly we conduct for the liquid sample. Yes, for the liquid sample we conduct, but for the solid sample, I still didn't find a way to design the reactor yet. Tell me if you know how to design. Yeah. Yeah, can. Liquid sample. Liquid sample. I mean, how? What do you mean? Uh, if the industry process, what is the process that you need microwave? You tell me. That one the strut is the what the biomass can be go through the conveyor belt also, but totally liquid sample. I don't know. I didn't see because if the liquid sample in the industry is a small scale, yes. Ah, yes, correct, correct. That one is a conveyor. Yeah, that one can see like the cement conveyor. Yes, yeah, because cement that one they heat up to 1001 degrees C. Yes, the 1001, the one industry skill. The what I talking about the lab skill, yeah. Industry that one, yeah, thousand, yeah, that one because I visited the cement factory before. Then they want to how to recover back the heat sources, but this is out of this topic. Recover the heat sources because he heat up to 1001, right? He you, still have remaining heat, so how to recover the heat? This one, but now the cement company or cement industry they also transforming. I mean they want to go more sustainable so that the every stage of the extra heat they need to recover back and up to around 200 degrees C then for the final samples. Yeah. Oh, you work in the cement industry? Yep. Anything? Yeah. We take a break for 15 minutes. So we come back later on. This is kinetic study. Yeah. Yeah, yeah. This is kinetic study. Yeah. You see, I follow this equation. Okay. I follow this equation, then I plot the graph. Plot the graph. This one got the graph. This one is yeah. This one is the rate of reaction. Then I plot the graph. Then after that, your experiment, I plot the graph. In Excel only, then from Excel, then they can know, they can calculate for you how many percent error. If less than, I can say less than 10%. So many more. Yeah, you have to, yeah. Can, 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 can. But not only that, this one true, but not only that, but you need to control the temperature. No, temperature. PID. Because you have the PID, you have to no control it. Separate PID. Yes, that one. Yes, yes. Correct. Correct. Then with this, then with the feedback system, we have put the thermocouple. Liquid product. Liquid product also. No. This one is a closed system. Closed system. No, this one. Liquid is inside here. Same, because this is a closed system. Closed system. We put it up. Correct. That one is pyrolysis. That one pyrolysis. Pyrolysis. Getting the char and liquid product. Correct. Yes. Yes. If you want to do for the certain purpose, we have to. Yes. Correct. For this one. Yeah, hello. So I think we can start the second session of the of today. Yeah, similarly, I will continue with the microalgae biomass to biochar. In this study, because in the previous study, we found that our focus is on the biochar. Then we found that the reducing sugar, the sugar content is produced. So in this study, we also convert that reducing sugar to bioethanol. At the same time, also the biochar that we obtain and we produce, and we do the further analysis. We found that it might be suitable for the bioabsorbent, and we also conduct the bioabsorbent study. So let us start this study. The instruction, I'm not going to go through the microalgae. I think all of you already know. The microalgae is able to fix the CO2 with the help of the sunlight. That one. Very good. Then this one is between. Again, we are using the wet perfection. Wet perfection. This is the comparison between the pyrolysis and also the wet perfection. Then this is the potential application of the biochar. It's almost similar, can be used as a bioabsorbent and also the solid fuel, and also for the carbon sequestration and as well as the soil amendments. This one is same thing. So we focus on the third generation of the microalgae to produce the bioethanol. Okay, the aims. The aims of this study is what to investigate the simultaneous production of the biochar and hydrolysis byproducts from the microalgae the chlorella using the wet production with microwave assisted acid hydrolysis. This is the first part. And the second part is how we going to convert the microalgae bioethanol productions from the acid restricted hydrolysis product from the first study. And the last one objective is to utilize the microalgae biochar as the bioabsorbent for the dye pollutants for wastewater treatment. Similarly, similar process, we are using the wet microalgae biomass with the household modified microwave assist heating wet perfections. Then we have two products. One is the solid biochar, another one is the liquid hydrolysis product. For the liquid hydrolysis product, we further analyze for the total reducing sugars concentration, and we found that it has the sufficient amount of the reducing sugar which enable us to convert into the bioethanol. And similarly for the biochar, we go to the proximate and ultimate analysis, the HSV, PGA, FPR, and SCM analysis, and see what is the potential applications. And in this study, we further analyze the bioabsorbent capabilities of the biochar that we produce. This is the household modified with the temperature 160 to 170, 5 to 10 minutes, just using one type of the acid, which is the sulfuric acid. Pressure maintained at 2.5 bar with energy input only 10 amperes. Yeah, this is the amount. The 20 gram of the microalgae we dilute with the 100 ml of the dilute sulfuric acids. Yeah, this is the amount that we are using. Just now, someone asking what is the amount that we are using. Then this is for the fermentation process. Each time we are just using the 50 ml of the microalgae hydrolysis solutions mixed with the yeast, the nutrient that we are using, the yeast, and also some nutrients for the yeast, which adjusted to pH around 4.6, suitable for the yeast to survive. So this This is the inoculum yeast that we are using, 1.5 gram per LS per liter. Then first with the nitrogen before the fermentation process. Then we control the environment at 29 degrees C with the non-aggregation stage using the dark fermentation. We are using the dark fermentation for this fermentation process. So this is the preparations for the absorbent study of the biochar on the dye pollutant uptake. So two types of the dye that we are using. One is the methylene blue and B the methylene blue and the conglomerate. This is most common dye pollutants happen in the wastewater. And to determine, we determine the final absorbent using the UVV with the wavelength between the 665 and 497 nanometers for the methylene blue and conglomerate respectively. So this is the method that we use to analyze the absorbent capabilities. So this is the preparation, the UVVs, microcentrifuges. This one is the thermocycle. So this is the calculations that we are using to analyze the biochar and also the percentage of the removal and also the absorbent capacity. So what is the maximum absorbent capacity that can take for the biochar? Then at the same time for the biochar, we analyze the SEM, see the pore size, what pore size, the porosities, and also the what is the surface areas, and also the PJC analysis to see whether what is the pH and also what is the charge for the for our biochar. So the effect of the absorption factor that we analyze is the pH. Whether the pH will affect the absorbent capacity or not, and also the bioabsorbent dosage and the initial concentrations and also the contact time. What is the total contact time in order for the biochar to absorb the maximum capacities of the dye pollutant. So we also adopt the isotherm models fitting to find the equivalent absorbent study to see the bioabsorbent capabilities. This is the three models that we are choosing. See which model can be fulfilled. I mean, in line with our study. Match well with our study. Okay, now go to the discussion. The first part of discussion is almost similar, but this time we are using the slightly different species. Here, the first species here using the Correda ESP31, and another one is the Correda GP. This is also another genetic modified species which rich in the protein. Then we found that from the previous study, we found that if the microalgae rich in the carbohydrate content, it has the advantage in the bioethanol production. So we have this hypothesis. So that's why we conduct this analysis. So after the wet correction, we found that this is a similar, almost similar result that we obtained from the previous study, with the increase of the acid concentration, the total biochar here is reducing. Of course, reducing with the different conditions, with all these conditions, the biochar here will be reduced. Similarly for these two species, the only difference is the degradation of the protein-rich microalgae is lower compared to the Correda ESP31, which is rich in the carbohydrates. At the same time, in this study, we analyzed the total reducing sugar. We found that the total reducing sugar is increasing. Why? Because the previous study we showed that the pathway is if we go through the wet corrections under the hydrolysis, the acid hydrolysis process, the carbohydrate content will be converted into the using sugar, using the glucose, using sugar. There are many glucose, so there are few compounds. So the total reducing sugar will be increased with the increase of the acid concentration. Yeah, this is in line with what we hypothesis from the previous study. Similarly, for these two species, but the only difference is what you see. The total reducing sugars for the carbohydrate rich, yeah, is around 100 grams. This one is around 20 grams only, which is this one is 5 times higher, 5 times higher. But we can make one hypothesis what? With the highest total reducing sugars, the total amount of the bioethanol can be converted is higher, right not? So this one we can convert into the bioethanol. While at the same time, we also look at the biochar. The biochar. Generally, the biochar, the heating values, the heating values for the biochar is increasing with the increase of the acid concentration for both species, But we can found that the carbohydrate rich microalgae, the increment of the HSP is highest compared to the another species, the Corella GP. This one only 23 increase to 22 increase to 23, only very small percentage. But while another species is increased close to 50%. 50%. Better for few properties. Then this one is for the energy yield. The energy yield is reducing for both species also same. Reduce with the total acid concentration increase. This one nothing much. Yeah, this one might be suitable for the solid fuel. So this one is what the derived crop for the TGA on the raw biomass and biochar. The weight loss occur between the 100 to 300 degrees C is due to the what? Decomposition of the carbohydrate and also the protein. This one here. Here, the peak is come from here. So this is the SEM analysis. So because you see this one is the before wet torrefaction, this one after wet torrefaction, we can see the porous is increased. This one is how many times? I forgot already. This one 2000. It's up to the 50 microns. I don't know how many times already. It's not mistaken 5. You see, you can see the porosity is increased very clearly increased. So yeah, so this is what we found. The outcome is almost similar with what we found from the previous study. The co-production of the microalgae biochar and also the sugar can be recovered for further bioethanol production by using the microwave assisted wet production from the microalgae biomass. Then the Corella ESP31 has the high total reducing sugar, which up to 98 grams per liter compared to another species. But however, another species has the high biochar yield up to 74%. 74% compared to Corella ESP. And the microalgae biochar after wet preparation, the HSP is increased potential for the alternative solid fuel. Then the porosity structure. So make them it's interesting to further study about the bioabsorbent. See whether it really can absorb some pollutant or not. This why. So, but one interesting finding is what? Similarly, from the previous study, we also found that the 5-HSM will be produced right now from the pathway that I show you. The 5-HSM will be produced in the hydrolysis after the wet torrefaction process. The 5-HSM, the amount of the 5-HSM also increase with the increase of the acid concentration, which we found that Chlorella ESP has also higher amount of the 5-HSM compared to the species, the Chlorella GD species, which is protein-rich microalgae. So this one as reducing sugar, this is produced as a byproduct. The higher severity of the acid, the greater degradation of the sugar into the formation of the 5-HSM. So sometimes, as I mentioned yesterday and the day before, the highest value not necessarily the optimum result, and you want to focus on what is your product, because like in this study, we found that yes, if we increasing the acid concentration, the reducing sugar might be increased. Right now, it's good for you to convert into the bioethanol, but at the same time, the 5-HSM will be produced. 5-HSM also one of the very good compound for the chemicals processing industry. However, later on I will show you what is the negative impact on the biodiesel, bioethanol production. You see, as we expected, if the highest reducing sugar it produce the highest bioethanol or ethanol concentration will be increased, right? Correct not? But it is not, because for this one, you see, for this one, why? Because it the fermentation condition is unfavorable for the bioethanol. Why? Because we have the 5-HMS. The 5-HMS is the toxic inhibitor, for the yeast. So make the fermentation process fail. Understand not? So that's why, because the amount of the 5-HNF is already reached the maximum tolerance limit of the yeast or for your fermentation condition. So that's why the ethanol concentration at this point or these 2 points are lower. So the highest value is not necessarily the optimal value. So we need to see what is the optimal value of the product that you want to obtain. That's the thing. So this is the discussion. So the ESP is potential candidate for bioethanol. So the bioethanol can be obtained with 7%. 7% is a very good amount. If considering this is the byproduct that we want to obtain from it. However, the 5-HMF can be the toxic inhibitors for the fermentation process. But this compound is very useful in the biofuel. Why is it it's very useful in the biofuel conversion as a fuel additive or as a polymer or resin for the prosecution in any chemical process. So in the future, we might be considered to extract or to separate out the 5-HMF before go to the fermentation process. So this is what we learned from this study. Then another second part is what? This is the SEM study with 500 times. This one is 500 times. We found that they are the biochar produced. They have the microporous material, which is the pore diameter is less than 2 nanometers. Then the BET surface area is around 2.65 meter square per gram, which make them is the suitable to be used as the bioabsorbents. Yep. So that's why. Then we conduct the PZC test. The PZC test, we found that the biochar that produced have the pH 3.7. If the pH more than 3.7, it have the negative charge. have the negative charge. That means what? If the pH more than 3.7, it can attract the cationic dial, which is the methylene blue, cationic dial, methylene blue. If the pH less than 3.7, it has the positive charge for the biochar, which is suitable for the anionic dye, which is favorite for the conglomerate color. This one methylene blue color. This one is wrong. So this one is we just do the see the initial pH, initial pH. So this one also we study, we also study the effect, one by one, effect. See what is the correlation between the just effect. The first effect we study is about the pH, with the initial condition with around 50 ppm. The absorbent dosage is about 5 grams per liter, with the agitation rate of 150 rpm and temperature 30 degrees, which is the room temperature, with the equivalent time 120 hours for methylene blue and 24 hours for the conglomerate. So we found that the removal percentage for both for both dye can reach more than 90% easily, no matter what is the pH, what is the pH. Then we want to see, what is the effect of the absorbent dosage, the initial dosage, which we found that the for the this one methylene blue, for the methylene blue, the absorbent dosage is 1 gram per liter, which it can reach up to 85% already. The removal can reach up to 85%. Yeah, which remove around nearly 40 milligram per gram of the methylene blue pollutant. While for the conglomerate, it can reach up to 95%, which equivalent to the 23.77 milligram per gram of the conglomerate dye at 2 gram dosage, 2 gram per liter, the dosage. This is what we found. However, the effective contact time is increasing. It's increasing from time to time. It's increasing. The removal of the methylene blue, which is optimum percentage at around 120 hours, with more than 80%. Then this one is in minutes, but for the conglomerate, after 4 hours, it almost can reach up to the 100%, for the 10 ppm, then more than 80% for other ppm. So the optimum contact time, or the optimal effective contact time is around 4 hours. 4 hours if you want to remove the conglomerate color. So this one is what is the model that check the absorbent capability that we are following. So for this study, we use 3 isotherms. One is long meal. This one, these two, another 2. 10 kings also, so see which one is closer curve to our absorbent capability. So this is our experiment data, and we plot the graph, and we found that the Romeo, the Romeo isotope model is closer. Both I can say all is almost similar, but the Romeo is isotope is assumed to be the closer to our biochar absorbent, so it can follow the Romeo equations. So from here, we found that what The microalgae biochar is the microporous absorbent with the diameter 4 diameter 0.665 nm. And the optimal absorbent for the both dye, methylene blue or the conglomerate is at the neutral pH. So we don't need to modify the pH of the biochar. So for the dosage is 1 gram and 2 grams per liter for the methylene blue and conglomerate respectively. And effective contact hour is 120 hours and 4 hours for the conglomerate. And the maximum absorbent capability is what 113 milligrams per gram, and also 165 64 to 65 milligrams per gram. So the long-meal isotherm model show the best fit with the absorption which belong to the monolayer for the methylene blue and conglomerate for our biochar. Yeah. So this is the short conclusion. I mean, from this study, we found that after the wet torrefaction, the liquid product are able to convert into the bioethanol. At the same time, we can get our biochar, which the biochar is suitable. It's one of the potential bioabsorbents for the dye wastewater treatment. So this is what we found. I mean, a standard study from the real study. Yep. Sorry. Limon reference, yes. Methylene blue, methylene 120 hours, yes. Yes, correct. 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 So that's why this is the experimental study. So from this study, we found that the conglomerate might be more suitable. I mean, this biochar is more suitable for the conglomerate. It might not be very suitable, even though it has the absorbent capabilities for the methylene blue, but it takes up to 120 hours to reach its optimum condition. So might not be feasible in industry. So this is what we found in our study. This we found. I didn't claim that our biochar is the best for the bioabsorbent. No, definitely this is not. We just made the conclusion it has the potential. Yes, the potential. Maybe in future we need to modify the biochar so that it can be more suitable for the certain absorbents. Yeah, bioabsorbent. Yeah, that's the thing. Yep. Yeah, I'm agree. 120 hours is not feasible in industry. Definitely not. Yep. Yes, correct. This one we conduct at the room temperature 30 degrees C only. 30 degrees. Discussion 2.2. Yes, yeah. Yes, correct. I can show you the graph. Here, 74%. Yeah. Here, the U. Yep. So, yeah. Because this one is a protein-rich microalgae, so the degradation not really took place under the torrefaction. So yeah. After the maybe this one we just conduct 5 to 10 minutes at 160 degrees C. Yes, correct. Yes, correct. Correct. Might be possible. Yes, correct. You are right. You are right. Yep, you are right. So this one because similar outcome that we found from the previous study. We found that the wet chloroplankton has less impact on the protein-rich microalgae. Yeah, that's why. Yeah, what you mentioned is correct. Yep, we do agree. Yep. The porosity we did this one. Yes. Porosity, yes, it's as good as previous because this one we just use the use this one, the Correda GP, the second one. Why we use the second one, you know? Because our main aim is to convert into the solid fuel. For the first species, the HHV is increased up to around, it's not 30, like 20 or 30. It's suitable for the solid fuel, but for this species, it's not suitable. So we want to find what is the potential application. We found that it might be suitable for the bioabsorbent. Yeah, we found it. Yeah. Less than 2 nanometer, which we found it in average is 0.65. 0.65, but less than 2. We can say the yeah. Yes, microprocessors. Correct. Correct. Bigger. Correct. Yeah. Sometimes yeah, the porosity diameter is yeah. Dulu. The structure, yeah. Yeah. Correct. True. This one is what species? This one is ESP. Correct. So that's why they as I mentioned, because that species is less impact on the wet fraction. That's the thing. Correct. How many times? This one is a ESP. Just now is a GP. Yep. Any other questions, comments? Yep. If not, I will continue one thing because yesterday we are discussing this one we didn't. Yes. Yes, it's able to recover, but if it reach until the maximum absorbent capacity, then it cannot be absorbed anymore. Yeah, can be recovered, but after its maximum capacity, yeah. So we didn't study. We just study the absorbent capacity only. Yeah, yeah, it's possible. I think it might be possible, but we didn't further study on that. That maybe you all can study because I'm not an expert in that one. We just found what is the potential. The potential. Okay, so this one we stop halfway, but I don't want to discuss more about this one. This one is about the ultrasonic method. I just we know that the ultrasonic method also one method that can enhance the overall reactions on the spent coffee ground. This one spent coffee ground. So what I want to show you is yesterday I have another slide to show you this one. Since we have a little bit more time, you see, this one is another potential of the biomass. We use the Jatopa the oil. I have the one. Okay, this one. You see, we use the Jatopa seeds to extract the oil. Then it left over the Jatopa biomass. So we convert the Jatopa biomass into the carbon-based acid catalyst. To be used back in the esterification process and also the acidification process. Yep. Because we converted into the acid-based catalyst, which suitable to be used as the acid esterification process, then followed by the biodiesel process. So this is what I want to show you. So in this study, we want to investigate the preparation of the carbon acid catalyst from the Jatopa, the oil seed cake. Jatopa, the oil seed cake, which the Jatopa biomass that we already extracted the oil. Then to analyze the characteristics of the prepared carbon acid catalyst. Then last one to study the effectiveness of the carbon acid catalyst in the biodiesel production, which we use back in our biodiesel productions. So this is the methodology. You see, for the first one, we just dry it up to 24 hours. Then we do the carbonization at the appropriate temperature determined by the TGA for 4 hours. Then we soften it with the sulfuric acid at 90 degrees for the duration from 5 to 20 hours under the constant stirring condition. Then after we prepare the catalyst, we need to do a series of the characteristics. So any one of you are working on the catalyst? No. Any one of you? No. Yeah. If you want to develop or design a certain catalyst, there are a series of the characterizations we need to go through. For example, the SEN, the PET, the EXT. This one a series of the characteristics I need to go through to make sure the catalyst that we produce is the desired catalyst. Yeah. So lastly, we study the reaction study, which we use the catalyst in our process. Then lastly, we see the reusability of the catalyst. Reusability. So the catalyst reusability to see whether it can be used up to how many cycles before it's reaching. So this is the result. So this is the TGA analysis of the Jatopa, the oil seed. So yeah, as usual, we know for those conduct the TGA, we know that the first 100 to 120 degrees is what the loss of the waters. Then another one is what is the indicate the degradation curve between this one is 350 to 450. You see, degradation happens. So with this, we choose 350 degrees C. Only the partially carbonized of the seed cake. Because why? We don't want to break down the micro molecule and remove the organic portion. We don't want that happen. So we only calcinate at around 350 degrees C. We don't want to break the structures for that catalyst. So this is how we do the sulfurizations at 5 to 20 hours. But after we conduct, we found that the total acid content already reach its optimum condition at around 5 hours. So we just use 5 hours, which the total acid can be reached up to 2.24 more per gram, more per gram. So there are no any significant increase in acidity. So that's why we do the carbonization at 350 C and also the sulfonication at 5 hours. So this is the SEN image of activated carbon, which is the acid catalyst. We plan to use the acid catalyst. So the pore volume is around 3.6 mm square. Then the pore diameter is 6.77 millimeters. Both same for the carbon and also the catalyst. Yes. Decrease with the decrease in the surface area. Correct. Yeah, why decrease in the surface area, right? Yeah, this one decrease in surface area. The pore size is almost similar. Yeah. This one we need to check why is yeah, yes. This one with the activation, this one we put in the acid, yeah. We put in with the acid. So the total surface area is just 1.92 millimeter square per gram compared to the just the carbon. I mean this one is from and also the pore volume is around almost similar. I can say 3.6 and 3.22 millimeters and mm cube per gram. Then we have the acid around 2.25 because we want to convert it into the acid catalyst. Acid catalyst. This one is the what? Our own jatopa oil. Yeah. Our own, we convert our on this one, the own jatopa seed after extract. Yeah, this one. We carbonize at 350 degrees C to convert it into the catalyst, to develop the own catalyst. Then this one is the functional group. It's not very okay. Then after that, we do the reaction study. We found that if by using our own prepared catalyst, it found that it also effectively can be convert the biodiesel up to the conversion yield of close to 100%, which is 99% at 7.5 of the catalyst loadings, with the methanol ratio around 12 to 1, which almost 99%. Then this one, the temperature we are using is around 60 degrees C, which is quite common for the biodiesel conversion, which the 60 degree is the optimum. So that means by using our own catalyst is also able to achieve the similar result. Then the conversion yield for the reaction time is around 1 hour. It's also same. It's also similar by using our catalyst. However, when we do the reusability, so after we use the first cycle, it can reach up to 99% based on the previous result. But after the second cycle, it's only the conversion here is only 96%, then 90%, 81%. So we would recommend, because after the fourth cycle it's reduced more than 10%, more than 10% of the, you see this 90, around 10% of the year. So we recommend to have the possible to regeneration of the sulfurification process of our catalyst. So the good thing is to use this solid catalyst compared to the liquid catalyst. What the solid catalyst can be reused, then easy to separate, because currently industry are using the acid liquid acid catalyst. So that's the thing. But the thing is, after the third cycle, we need to reactivate the catalyst. So this is the this is the second step. This is not so important already, because after that we just prove that the acid, the biodiesel that we produce also almost similar with what we produce by using the conversional process and conversional catalyst. So this is the conclusions. This can recommend to use up to four cycle, but I would recommend use up to 3 cycle. Then we can be activated, and the biodiesel here can be achieved up to 96%. Is almost similar. Then the biodiesel that we produce also fulfill the STM and EN standard at 6.1, 6.1 or 12.1 methanol to oil, 6 to 1, the one is 12 to 1, right? I still remember. 6 to 1 is not the highest, to be 12.1, I think. I think it's to be 12. 12. Normally it's 12. It's not 6. It's 12 to 1. To be 12 to 1. 12 to 1, you see here. Hey, no. It might be 6. This one is the second step already. Let me see. Oh, 6 to 1. Because 6 to 1. This one is the second stage. It's the triacidification. 6 to 1. 6 to 1. This second step, not the first step. Second step. 6 to 1 is correct. 12 to 1 is the first stage, is the acid acidification. Yes. Correct. These are 6 to 1. Correct. This one is 12 to 1. Yep. So from this study, we found that the two findings. The jatopa, the oil, can be converted into the acid catalyst, which is better for the process. Why? Because the catalyst can be separate easily, then can be used back. Yeah, that is the thing. Yep. Any questions? Some potential application. Any questions? Yep. If not, I think today we just end here, because this one is heterogeneous catalyst. Heterogeneous catalyst, so that the benefit for the heterogeneous catalyst is what? Easy for separation. Easy for separation. And this one is we can develop our own homogeneous catalyst, which is quite stable for the process. Why I say stable? Because you see, we are carbonized at 350 degrees C. That means what? It will not transform or change the phase up to the 300 degrees C, and we use our catalyst at around 60 degrees C only, because the reaction for the acidification is around 60 degrees C. It's quite stable. It's quite stable and sufficient to be used as a catalyst in that process. They're quite easy and simple, because for the acid catalyst acidification process, we just need to put in the acidics into the process only. That's it. No, this catalyst compared to what? Okay. No, we put it that way. Of course, the current commercial catalyst is still better. If we are talking about the homogeneous catalyst. Homogeneous catalyst is still better. Of course, it means by the industry process, still better, but it cannot be recovered. Some of the process we need to recover because some of the process why we need to recover, they need to get the pure products. That one can be recovered easily. Yes, correct. This one thing. Then second thing, reduce the overall cost. Overall cost, I mean, we need it. Because it can recover. That one, if even though for the homogeneous catalyst, you don't want to recover, you just keep putting. Yeah. Just keep at the normal condition because it's not transformed or whatever at the room temperature. It's quite stable. For the solid gas, it's quite stable because we activated up to the 350 degrees C. That means at the room temperature is really quite stable. Quite stable. Then we sulfurification, make the sulfurification at around 90 degrees C. So as long as it's not heat up to the 80 to 90 degrees C, I think it's quite stable. Yeah, at the room temperature. I mean, at the room temperature. Yep. Mm. Mm. Yes, yes, correct. Yeah, that is the thing that facing by not only the as a bioabsorbent, it's at many other purpose. You see our water filter and all these things. How we going to recycle? So this is what we need to think. So how you see if that absorbent to absorb something that useful, then we can recover. Heavy metal can recover. If we use the biochar to example only to to absorb the heavy metal. Then from that we can find a way to extract up the heavy metal. Then for other purpose. Then for the dye, I don't know what is the purpose. Yes, what we going to use yet. Similarly, you see now people is looking for the what material to store the hydrocarbons. I ask them, they can put in how they extract the hydrogen out. They can keep storing. Similarly, they do the carbon capture materials. They just put in the carbon, store there, not solve the problem. Then if you want to use, how to restore back? Ah, ah, correct, correct, correct. That's the thing. Correct, correct. Yes, correct. This is what I tell you. So that's what I pointed out. More and more similar problem that you mentioned. Like you mentioned. Yeah, more and more problem because carbon captures is a very hot topic. But only the carbon capture for me, for my point of view, and for many scientists around the world, especially you know the what professor, what's the name already? The editor of the RSER, he mentioned one thing here. He do the analysis of all the potential, she is a she, potential green technology. She found that we found that the carbon capture really cannot help the world because Jesus keep storing. But the carbon capture with the utilization, how we going to use it? Because we just store it, but for what and how? Yes. Less sulfur. Desulfurization, yes. Oh, you want to use a coal as a catalyst or what? I know, yeah. And mm, yeah, that one also, yeah. That's why it depends on the application. So that's why, if possible, should be make it no sulfur. It's possible. But you see, if you want to use as a pyrolysis, pyrolysis process is burn until very high temperature, the sulfur might be released, correct or not? Released. So until which stage is really depend on you. What type of what is the quality of the catalyst that you want to produce? I can give you one example. The biogas. Normally, the biogas from what already? Biogas. Yes, correct. They contain a lot of the sulfur. Sulfur will be produced. So before they use the biogas, they do the desulfurization to correct the sulfur, because sulfur is a very useful product, right? Not if we able to recover back the sulfur. Sulfur is useful in the many industries applications. So we need to do the desulfurization before we use the biogas. If not, it will harmful to the environment. That is the thing. So how much you want to do the desulfurization, it really depends on the process and what you want. What is the standard that in your country or in your region. Correct. That's the thing. We need to do the desulfurization. So it really depends on you. What is the regulations is a lot of your country, but ideal case should be no. I mean, cannot be no. Ideal case should be no. Like so we try to desulfur as much as possible, because if not, in many green energies, in green energy, it will release the sulfur, even though the hydro energy, the hydro energy around the hydro dam is contain a lot of sulfur. If you have chance to visit any hydropower plant, you can see surrounding area all in yellow color, yellow color sulfur release. Yeah, sulfur release. Why release? Because you see the hydro water go down to the land, then the sulfur from the ground release. That's the thing. Leaching. Leaching. Yeah. Soil. Yes. Soil, because the reaction between the soil and water. Because from high. Yeah. Oh, think I visited highway. Oh, yellow color. Yellow color. Yeah. That's the thing. Yes. Yes. Soil. Yes. So yeah. Any other questions? Neutral. Hmm. That one is I another one. This one. This one. Oh, this one I mentioned I use the neutral biochar. Which one? Which slide? Biochar you. This one. Not this. No. Is it this slide or another slide? Biochar you. This one. No, no, no. This one before. Oh, this one acidic one. Acidic one. Three. If not mistaken, biochar that produced for this one is 3.7. Yeah. Three. That means the final biochar the is acidic is 3.7. Yeah. Final biochar. I mean for this specific is acidic in nature. Acidic in nature. 3.7. This one is not for this one no. Particular for this one is no. For particular, but for the previous one, the Jatopa one is yes. Because I didn't add any acid at the beginning, neutral. Then after that, I add the sulfurication process. I add the acid straight, then become acidic. Yeah. Adjustment. No. I didn't do any adjustment, but we also did do the adjustment. Not to say do the adjustment. See what is the effect of the pH. That one. See the effect of the pH. Then we do the adjustment. But after that, we didn't do the adjustment because it's why. You see this one. BB size 3.7 acidic. Then this one. We do the different pH. Yeah, it found that nothing much different. Nothing much different. So after that, we didn't do the adjustment. So we just use their natural pH. Natural pH, which is acidic pH. Yep. So that's why the conclusion also mentioned that it's best fit. Oh, that's natural pH. Yeah, natural pH. Yeah. Okay, I think that's all for today. So yeah, see you tomorrow.
Hello everyone. Thank you, sir, for today's session. And today's session is formally over. And within 5 minutes, we'll start our lunch. And for tomorrow, the first session will be taken by Dr. Remya ma'am. and which will be followed by Ong sir's lecture post tea break. And after the lunch break tomorrow, we will have a lab visit, maybe around from 2 o'clock onwards. And thank you. So within 5 minutes, we'll be going for lunch. So if you want to have any informal discussion with sir is thank you.
you.